everyone. Today we are diving deep into Azure OpenAI Service, covering complete setup and cost management strategies that you can apply in production environments. Over the next session, we'll walk through the entire journey from provisioning your first Azure OpenAI resource all the way to building a production-ready systems with comprehensive cost controls and monitoring. We'll cover authentication strategies, deployment patterns, optimization techniques, and the operational practices that separate prototype implementations from systems that can handle enterprise scale workloads. This is a practical hands on knowledge based on real production deployments, and by the end, you will have a clear roadmap for implementing Azure OpenAI in your own infrastructure. So let's get started. About why we would choose Azure OpenAI Service over other options for accessing OpenAI models. Azure OpenAI Service provides enterprise-grade access to OpenAI models with Microsoft's infrastructure guarantees. This is important when you are building production systems that need reliability and compliance. The first key differentiator is enterprise SLAs. You would get a 99.9 uptime guarantee with financial backing. This means if Microsoft doesn't meet the availability target, you'll get service credits. For production applications where downtime has real business impact, this SLA provides accountability that you don't typically get with other API services. Second is regional deployment. You can deploy models in your preferred Azure regions. This matters for two reasons: latency and data residency. If your users are in Europe, you can deploy there. If you have regulatory requirements about where the data is processed, you have control over that as well. Third is private networking. Azure OpenAI integrates with VNet and supports private endpoints. This means your API calls never traverse the public internet. For organizations with strict security requirements, this is often a non-negotiable requirement. Fourth is compliance. The infrastructure is HIPAA, SOC 2, and ISO 27001 certified. If you're in healthcare, finance, or other regulated industries, you inherit these certifications rather than having to audit third-party APIs. And the fifth is cost controls. You get spending limits, quota management, and regional pricing options. You can set hard caps on spending, allocate quota across different teams or applications, and choose regions with lower pricing. Organizations typically choose Azure OpenAI when they need guaranteed availability, regulated compliance, and integration with the existing Azure infrastructure. The managed service abstracts model hosting complexity while providing enterprise controls that you would otherwise have to build yourself. So now let's look at the architecture overview to understand how these components fit together. The service sits between your application and OpenAI's models. You create resource instances in Azure and deploy specific models to those resources and access them via REST APIs or SDKs. Each deployment has independent scaling and quota controls. Let's look at this diagram. Your application sends requests to Azure API Management, which can provide additional capabilities like request throttling, authentication, and logging. Then it routes to Azure OpenAI Service, which is a managed service hosting the models. Within Azure OpenAI Service, you can have multiple deployments. You might deploy GPT-4, GPT 3.5, or even GPT-5 thinking and embedding models. Each has a separate deployment. Each of these deployments connects to a model endpoint that actually serves the request. The key thing to understand here is that deployments are isolated from each other. If you allocate 20,000 tokens per minute to your GPT-4 deployment and it gets saturated, this does not affect your GPT 3.5 deployment. This isolation is critical for production systems where you want to prevent one workload from impacting another. Let's start with the first step, which is creating your Azure OpenAI resource. The first thing we have to navigate to the Azure portal and create a new Azure OpenAI resource. During creation, you need to make several selections that will impact your deployment. The very first selection is a subscription. This is the Azure subscription that will be built for usage. The second is a resource group. This is a logical container for related resources. I typically recommend creating a dedicated resource group for your AI workloads so you can manage permissions, costs, and lifecycle together. The third is region. You should choose this based on the latency and compliance requirements. If your users are primarily in North America, East US, or West US, then it makes sense. If you're in Europe, then West Europe or North Europe will make sense. Production workloads, you will use standard, and there is only one pricing tier currently, but it's more important to select it correctly during provisioning. Now, region selection really matters here. Model availability varies significantly by region. GPT-4 deployments are available in limited regions like East US, Western US, and Japan East. You should check current availability before provisioning because this changes quarterly as Microsoft expands capacity. If you provision a region that does not support the model you need, you'll have to create a new resource in a different region and migrate your application, which is pretty time consuming. So verify the model availability first. Let's walk through what happens after you submit the resource creation. The provisioning flow goes through the several steps as outlined here. First, you'll select your subscription, then you choose your region, then you create the resource, and then you wait for the deployment, which typically takes about 2 to 3 minutes, and finally, you retrieve your keys and endpoint. After resource creation completes, you'll navigate to the resource in the portal and retrieve your endpoint URL and access keys. You'll need this for API authentication. The endpoint follows a very specific format, for example, HTTPS your resource name.openai.azure.com, where your resource name is the name you gave your resource during the creation. Now, an important security practice here. You should store these credentials in Azure Key Vault rather than in application configuration files. Putting credentials in configuration files, even if they are not checked into source control, creates security risks. Key Vault provides a centralized secret management, automatic secret rotation capabilities, and audit logging, which are pretty important in production use cases. Your application should retrieve the credentials from Key Vault at the startup rather than having hard-coded them in somewhere in the source code or even the configuration files. Once you have your Azure OpenAI resource created, the next step is the deploying models. In Azure OpenAI, you don't just get access to models automatically. You explicitly deploy models to your resource. And this gives you fine-grained control over which models are available and how much quota each one gets. Looking at this diagram, your Azure OpenAI resource can host multiple deployments. You might deploy GPT-4, GPT-3.5, GPT-5, or even embedding models. Each deployment then gets allocated a portion of your total TPM quota, which is tokens per minute. Each model deployment requires several configuration decisions. So the first one is deployment name. This is a user-defined identifier that you will reference in your API calls. I recommend using descriptive names like GPT-4 production or GPT-3.5 turbo dev, so it's clear what each deployment is for. The second is model selection. You choose a specific model number, like for example, model version like GPT-4 Model versions are dated and newer versions are released periodically with improvements. The third is the TPM quota. This is your tokens per minute allocation from your subscription's total quota, and we'll talk about quota management just in a bit in a few slides. And the fourth one is version binning. You need to decide between auto update, where Microsoft automatically updates your deployment to newer model versions, or static version, where you stay on a specific version until you manually update. Now, here's something that's really useful for production systems. You can deploy the same model multiple times with different quotas. For example, you might have a GPT-4 production with, let's say, 60,000 TPM and GPT-4 development with 10,000 TPM. This provides workload isolation. If your development team is doing heavy testing, they can't accidentally consume all the quota, and that's how we protect the production traffic. Now let's talk about authentication, which is how your application proves it has the permission to use your Azure OpenAI resource. These are two authentication methods available, and the choice between them has significant security implications. The method one is API key authentication. This is simpler but less secure. Here's what the code looks like. You create an OpenAI client, pass in the URL of your resource, and pass in an Azure key credential containing your API key. This works fine for prototypes and development, but there are security concerns for production. API keys are long-lived credentials. If someone gets your API key, they have full access to your resource until you manually rotate the key. There's no automatic rotation, no fine-grained permissions, and limited audit visibility into which application or person made that API call. The method 2 is Azure AD authentication, which I strongly recommend for production. Here's what the code looks like. You create a default Azure credential which automatically picks up the identity from the environment and pass that to the OpenAI client. Azure AD authentication enables managed identities, which eliminates the credential storage entirely. Your application's identity is granted access through Azure RBAC roles. You would typically assign either the Cognitive Service OpenAI user role for read access or Cognitive Services OpenAI contributor role for administrative access. The key benefits here are automatic credential rotation, fine-grained permissions through RBAC, and comprehensive audit logging. You can see exactly which managed entity made which API call and when. For production systems, especially in regulated industries, this audit trail is often required. Now let's look at the code to actually make an API call to Azure OpenAI. Here's a complete example in JavaScript. First, you require the Azure OpenAI SDK. Then you set your endpoint, which is a resource URL. Then you set your API key. And then you set your deployment name, which references the specific model deployment you created earlier. You create a client using the endpoint and key credential. Then you call get chat completions, passing your deployment name, an array of messages, and an options object with parameters. The messages array contains your conversation. The system message defines the assistant's behavior. I have set it to you are a helpful assistant. The user message is the actual question or the prompt. In the options, max token limits the response length to 100 tokens and the temperature controls randomness. The temperature ranges from 0 to 2. 0 gives you more deterministic, focused responses. 2 gives you more creative, varied responses. 0.7 is the balanced middle ground that works well for most applications. The response comes back with a completion, token usage, and metadata. You extract the generated text from the result.choices, zero.message.content, and the key parameters to understand here are temperature, max tokens, and deployment name. Temperature controls the randomness and creativity of the responses. Max token limits the response length, which directly impacts cost since you pay per token. And deployment name references which model deployment you use, which determines both capabilities and quota allocation. Now let me walk through the complete request flow so you can understand what happens when you make an API call. The flow starts with initializing your client with authentication credentials, then you select which deployment you use, then you configure the parameters like temperature and max tokens, then you send the request, and then you handle the response from the service, and finally you parse the completion from the response object. Your application authenticates with the endpoint, either using an API key or Azure AD token. Then it specifies which deployed model to use by passing the deployment name. Then it sends the prompt along with the configuration parameters. The service processes the request and returns a response object containing the completion, token usage details, and metadata like finish reason. Response processing is pretty straightforward. You extract the generated text from the choices array. Choices in an array because you can request multiple completions from the same prompt by setting the end parameter. Though typically you just request one and use choices 0. The response also includes token usage information, which tells you how many prompt tokens and completion tokens were consumed. This is important for cost tracking, which we'll cover in just a few slides. Now let's talk about the security best practices because there are several important configurations you should implement for production deployments. On the network security side, there are 4 key practices. So the first is private endpoints. You should route the traffic through Azure VNet so it never touches the public internet. This eliminates the exposure to internet-based attacks. The second is VNet service endpoints. You can restrict the service access to specific VNets. Even if someone has valid credentials, they can't access the resource unless they are on an approved network. The third is IP allow listing. You can configure firewall rules to allow only known IP ranges. This is helpful if you need applications running outside Azure that need access. And the fourth is disabling public access entirely. You can configure your resource to require private endpoint for all connections. This is the most secure configuration and is often required in regulated industries. On the identity and access management side, there are 4 key practices. So the first one is manage identities. So you should assign Azure AD identities to services like App Service, Azure Functions, or AKS. These services can then authenticate to Azure OpenAI without any stored credentials. The second is RBAC roles. You should use least privilege access with built-in roles. Don't give everyone contributor access. Use the OpenAI user role for applications that just need to make the API calls. The third is key rotation. If you're using API keys, you should automate rotation for every, let's say, 90 days. Azure OpenAI provides 2 keys so you can rotate them without downtime. And the fourth is audit logging. You should enable diagnostic settings to track all API calls. This creates an audit trail that showing who accessed what and when. Now let me show you what a zero trust architecture looks like with Azure OpenAI. In this setup, your application authenticates via managed identity. It doesn't have any stored credentials. Azure AD validates the permissions through RBAC to verify the application has the right role assignments. Then traffic flows through private endpoints within your VNet. The traffic never touches the public internet. No API keys are stored in application code or configuration. All access is logged to Azure Monitor for compliance auditing. If you need to revoke access, you just remove the RBAC role assignment. The application immediately loses access without any code changes or the redeployment. The architecture provides several benefits. First, there is no credential management burden, no keys to rotate, no secrets to secure. Second, there is granular access control. You can grant access at the resource level, deployment level, or even operational level. Third, there is comprehensive audit trail. Every API call is logged with the identity that made it. And fourth, there is immediate revocation capability. So remove the role assignment and access is immediately revoked. For production systems, especially in enterprises with security requirements, this is the architecture you should be implementing rather than using API keys. Now let's talk about cost, which is pretty critical for production Azure OpenAI deployments because cost can scale quickly if not managed properly. Azure OpenAI pricing has three main components you need to understand. The first component is token-based pricing. Input tokens, which are your prompts, are built per 1,000 tokens. Output tokens, which are the completions, are also built per 1,000 tokens. The rates vary pretty significantly by model. GPT-4, for example, is much more expensive than GPT 3.5 Turbo for both input and output. The second component is model-specific rates. GPT-4 has higher costs for both input and output tokens if it's more capable, so it commands premium pricing. GPT 3.5 Turbo has lower costs and is suitable for high volume applications where you don't need GPT-4's advanced reasoning. Embeddings are charged per 1,000 tokens processed, and they are generally the cheapest operation. The third component is regional pricing. Prices vary by Azure region. Some regions offer 20 to 30% lower rates for the same model. This is typically driven by capacity availability. Regions with newer data centers or more capacity might have promotional pricing. Now, here's the critical context. These rates change periodically as Microsoft adjusts its pricing and as new models are released. You should design your cost management strategy around relative pricing patterns rather than the absolute numbers. Understand that GPT-4 will always be more expensive than GPT 3.5. Understand that the output tokens always will cost more than the input tokens. I understand that the regional differences do exist. But don't build your architecture around specific dollar amounts that might change next quarter. This architecture can look like. The flow starts when a request comes in. Before you actually call Azure OpenAI, you should estimate token counts. Then you predict costs based on current pricing. Then you check against the budget limits, and then you make a decision. If you're under the limit, you can execute the call. If you're over the limit, you either queue the request for later processing or reject it entirely. After executing the call, you log usage details to a database or analytics system. Then you feed this into the cost analytics dashboards that you show spending trends on. The key insight here is that we have to be very proactive with our cost control. You're estimating and checking before and making any API calls here rather than discovering the overspending after the fact. Estimating the token counts is reasonably accurate. For English context, you can estimate roughly 4 characters per token. So a 1,000 character prompt is roughly about 20 to 50 tokens. There are also tokenizer libraries that give you the exact counts. Predicting cost requires maintaining current pricing data. You can hardcode relative costs or query Azure pricing APIs programmatically. For example, you might store that GPT-4 output tokens cost roughly 6 times more than GPT 3.5 output tokens. Budget checks should happen at multiple levels. You might have a daily budget, an hourly budget, and a per user budget. If any threshold is exceeded, you take action. This prevents unexpected overruns in high traffic scenarios when a single busy hour could consume an entire day's budget. Now let's talk about specific cost optimization strategies, starting with the prompt engineering, which is often the highest ROI. Inefficient prompts can consume up to 2 to 3 times more tokens than necessary. Small optimizations in how you structure the prompts compound across thousands or millions of API calls. There are 4 key optimization techniques. So the first one is removing redundancy. In a multi-turn conversations, you should eliminate repeated context. Don't spend the entire conversation history if your only recent message is irrelevant. Summarize the older context or drop it entirely. The second is using system messages. You should define the system's behavior once in the system message rather than repeating the instructions in every user message. The system message is processed once and influences all responses without being repeated. The third is concise instructions. Instead of verbose explanations, use direct instructions. Summarize, let's say, in 3 sentences is much better than, let's say, saying, please provide a summary that is concise but informative, capturing the key points in approximately, let's say, 3 sentences. So try to be more direct with instructions rather than having it be multiple sentences. And the fourth is stop sequences. You should define clear completion signals to prevent overgeneration. If you're generating structured data, you can include a stop sequence so the model stops immediately after completing the structure rather than continuing to generate additional content. Here's a real world impact example. A customer support chatbot reduced average tokens per conversation from 850 to 320 by optimizing the system prompts and removing the redundant context. They reviewed their conversation logs, identified repeated phrases and instructions, moved behavior definitions to a system message, and stopped sending entire conversation histories when only the last few messages mattered. This translated to about 60% of cost reduction while maintaining response quality. The responses were just as good, and they just used less fewer tokens to achieve the same result. So that's the power of prompt engineering. Now let's talk about the second most very important cost optimization strategy, which is intelligent model routing based on request complexity. Not every request requires GPT-4's levels of reasoning capabilities. GPT-4 is excellent for complex reasoning, but it costs significantly more than GPT 3.5 Turbo. If you route every request to GPT-4 when many could be handled by GPT 3.5, then you're overpaying. You should route requests based on the complexity assessment. For simple requests, use GPT 3.5 Turbo. This includes FAQs where the answer is straightforward, simple classification tasks, and straightforward text generation. For complex requests, use more complex reasoning models like GPT-4 and GPT-5. This includes complex reasoning tasks that requires multiple steps, multi-step tasks that need planning and execution, and high-stakes content where accuracy is very important. The key here is implementing classification logic that accurately identifies which requests need GPT-4 or more complex reasoning models. You might use heuristics like prompt length, presence of specific keywords, or lightweight classifier that categorizes the request type. In practice, you should be able to route 70 to 80% of your requests to simpler models like GPT 3.5 while reserving GPT-4 and GPT-5 like more complex models for genuinely complex scenarios. This can reduce the cost by 50 to 60% compared to just having all your requests directly go to complex reasoning models like GPT-4 or 5. The implementation typically looks like this. When the request comes in, you classify its complexity as simple or complex. You route the simple request to simpler models like GPT 3.5 deployment. You route the complex request to more capable models like GPT-4 or GPT-5 deployment, and then you execute the call, and then you evaluate whether the routing decision was correct. That evaluation feeds back into your improving your classification logic over time. The third major cost optimization strategy is response caching, which can have dramatic impact on certain workload types. For applications with repeated queries, caching can reduce costs substantially, particularly in FAQ style systems where users ask similar questions. The key insight is that if you have already paid to generate a response one, you shouldn't pay to generate the identical response again. The flow works like this. A request comes in, you generate a cache key from request parameters, you check if there is a cache hit. If yes, you return the cache response immediately, paying no API cost. If no, you call Azure OpenAI to generate a fresh response, then cache that response for future requests, and then return it to the user. Implementation typically uses Azure Cache for Redis, or just a standalone self-hosted Redis for distributed caching or in-memory caching for a single instance applications. For high traffic applications, Redis provides shared cache across multiple applications instances. The critical part here is the cache key design. You should hash the full prompt, including the system message, user message, and key parameters like temperature and max tokens. This ensures that the functionality is identical request returns the cache results. Even minor parameter differences should result in different cache keys because they might produce different responses. For FAQ style systems where users frequently ask the same questions, we have seen cache hit rates of 40 to 70%, which directly translates to cost reduction. If your cache hit rate is 60%, you're avoiding 60% of API calls, So you're essentially reducing your cost by 60%. However, cache effectiveness varies significantly by workload. Research applications where every query is unique might only see 10 to 20% cache hit rates. User generated content applications where every request is different might see almost no caching benefit at all. So the caching works best when your query distribution has a reputation. Now let me show you what the implementation code looks like for response caching. This is a C# example. So you have a method called getCompletion with cache that takes a prompt. The first thing you do here is to generate a cache key from the prompt. Then you check if there is a cache result for that key. If the cache is not null, meaning there is a hit, you return it immediately. This returns the response in milliseconds with zero API cost. If there is no cache hit, you make the actual API call to OpenAI. You get the response, you extract the content from the result, and then store it in the cache with an expiration time, and then return it to the user. The cache expiration strategy is important here. You should set the TTL, which is time to live, based on the content freshness requirements. Product descriptions that don't change often might cache for, let's say, 24 hours or even days. News summaries that become stale pretty quickly should expire in few hours. Dynamic content that changes frequently might only be cached for a few minutes. There is also a consideration around cache invalidation. When you update source documents, you need a strategy for invalidating related cache responses. You can't have users receiving cache responses based on old document versions. Some teams implement cache tagging, where all responses related to document share a tag, and when the document updates, they invalidate all the responses with that tag. Another consideration is cache forming. Before you have cache responses built up, your initial queries will be slower and more expensive. This cold start period is normal. For critical queries, you might proactively warm the cache by pre-generating the responses for common questions during low traffic periods. The fourth cost optimization strategy is the strategic max token configuration, which prevents runaway costs from overgeneration. Setting appropriate max tokens prevents scenarios where you expect a 50 token response, but the model generates 2000 tokens because it started generating examples, explanations, or additional content you did not need. You should set max tokens by use case based on what is actually required. So for classification tasks, 5 to 10 tokens is sufficient. You're typically getting back a category name or a simple yes or no. For short answers to factual questions, 50 to 100 tokens works well. This gives you a concise answer without unnecessary elaboration. For summaries, 150 to 300 tokens are depending on input length. Longer source content might need longer summaries, but you still want to cap it to prevent overgeneration. For long form content generation, 500 to 1500 tokens with clear justification for why you need that length. Most use cases do not need 1500 tokens. Here's the implementation pattern in JavaScript. You define an object mapping request types to token limits. Classification gets 10 tokens, QA gets 100 tokens, summary gets 250 tokens, and generation gets 800 tokens. Then when you make your API call, you select the max tokens based on request type. This prevents a classification request from accidentally consuming 2000 tokens if the model decides to generate a verbose explanation along with the classification. You have hard capped it at 10 tokens, so even if the model wants to generate more, it's cut off. This protects your budget from unexpected behavior and very high unexpected cost spikes. The fifth cost optimization strategy is streaming responses, which provides both user experience and cost benefits. The traditional approach is to wait for the entire completion before returning anything to the user. With streaming, you get tokens as they are generated. The flow looks like this. You send a request with streaming enabled. The first token arrives quickly. You stream each token to the user as it arrives. And then if the user stops reading or gets the answer early, you can cancel the stream, which saves token cost on the uncompleted portion. The key benefit is enabling an early termination. If a user gets the answer after 200 tokens, they can stop the stream rather than waiting for and paying for the full 1000 token completion you have configured as the max. In practice, streaming can reduce average token consumption by 10 to 20% in interactive applications where users don't always need full responses. However, this benefit only applies to interactive use cases. For batch processing or API to API calls, there is no early termination opportunity, so streaming does not reduce costs. Streaming also improves perceived latency. Users see the first token in perhaps 500 milliseconds rather than waiting full 5 seconds for the complete response. This creates a typewriter effect that feels more responsive even when the total generation time is similar. Here's what the streaming implementation looks like in JavaScript. You call stream chat completions instead of get chat completions. You pass the same parameters, deployment name, messages, and options, including max tokens. But instead of getting back to a complete response, you get back an async iterable of events. You iterate over the events using a for await loop. For each event, you look at the choices. For each choice, you extract the delta, which contains the incremental content. If there is delta content, you write it to the standard output, which displays it to the user immediately. The user experiences that text appears progressively, word by word, or phrase by phrase. This creates a typewriter effect that users find much more engaging than waiting for a complete response. For an implementation perspective, streaming is straightforward. Most Azure OpenAI SDKs provide streaming methods. You just iterate over the event stream and process each delta as it arrives. Error handling is pretty important though. If the stream is interrupted, or you need to handle that gracefully and potentially retry or inform the user that the response is incomplete. One note is that streaming and caching interact in an interesting way. You typically cache the complete response after streaming finishes. On cache hits, you might either return the complete cache response immediately or simulate streaming by sending the cache response in chunks to maintain consistent user experience. Now let's talk about Quota Management, which is how Azure AI OpenAI controls throughput to ensure fair resource allocation across customers. Your subscription has a total TPM quota, which is tokens per minute. You allocate this quota across deployments. Looking at this diagram, your subscription quota feeds into multiple deployments. Deployment 1 might be GPT-4 with 20,000 TPM. Deployment 2 might be GPT 3.5 60,000 TPM. And deployment 3 might be embeddings with 120k TPM. You should allocate quota based on expected traffic patterns and business priorities. Here's a sample allocation strategy. So for production GPT-4, you might allocate 40% of total quota. This is your highest priority workload that directly impacts customer experience. For production GPT 3.5, you might allocate another 40% of total quota. You're serving more requests than GPT with GPT 3.5 than GPT-4, so you do need significant quota for this as well. For development and testing, you might allocate 15% of total quota. This ensures your development team can work without impacting production, but they do have lower priority because it's not production use case. For embeddings, you might allocate 5% of the total quota. Embedding calls are typically less frequent than completions in most applications. The specific percentages depend on your workload, but the principle is to allocate based on business priority and expected usage patterns. You should monitor actual usage versus allocation monthly and rebalance as traffic patterns change. For example, if you notice your development deployment is consistently at 10% utilization while production is hitting quota limits, you might reallocate some development quota to production. The quota allocation isn't static, so you should be adjusting it based on your real world usage data. Now let's talk about what happens when you exceed your TPM quota and how to handle it gracefully. When you exceed TPM quota, Azure returns HTTP 429 status code with retry after headers. This tells your application that you have hit the rate limit and when you can retry next. You should implement exponential backoff for handling these errors. Here's a C# code for that. You have a method called getCompletion with retry that takes the prompt and max retries parameter, which defaults to 3. You loop up to max retries, you try to get the completion. If you succeed, you return it immediately. If you catch a request fail exception with status to 429, you calculate an exponential delay. On the first retry, you wait 2 to the power 0, which is 1 second. On the second retry, you wait 2 to the power 1, which is 2 seconds. On the third retry, you wait 2 to the power 2, which is 4 seconds. After waiting, you retry the request. If you have exhausted all retries, you throw an exception. The exponential backoff prevents your application from hammering the service with immediate retries, which would get rate limited again. By progressively increasing the delay, you give the quota window time to reset so that hopefully next time you don't hit into the retry, the 429 again. An alternative strategy for non-real-time workloads is to queue the request when you hit the rate limits. You could push the request to Azure Storage Queue or Service Bus, then process it asynchronously when your quota becomes available. This works well for batch processing where users are not waiting for responses. You can throttle the queue processor to stay under the quota limit and ensure steady progress without rate limiting errors. For real time user facing applications, exponential backup is better because users are waiting for responses. For background processing, queuing is often much more elegant because you can optimize throughput without concerning users with the repeated retries. So now let's talk about monitoring, which is pretty important for understanding usage patterns, identifying optimization opportunities, and controlling costs. You should enable diagnostic settings in Azure Monitor to collect detailed telemetry from your Azure OpenAI resource. There are four types of data you should be collecting. So the first is request logs. You want every API call logged with details like prompt length, completion length, and model used. This gives you visibility into every interaction. The second is token usage. You need detailed breakdown of input tokens versus output tokens for each request. This is essential for cost attribution and optimization analysis. The third is latency metrics. So you should track request duration from start to first token and total completion time. This helps identifying performance issues. And the fourth is error rates. You want to log 400 or 500 responses, HTTP responses by error type so you can identify issues like authentication failures, rate limiting, or service problems. For storage, you have three main options. So the first option is Log Analytics Workspace. This lets you query logs with KQL, which is Queue to Query language for data analysis. You can aggregate, filter, and visualize your data. The second option is Storage Account for long-term retention. If you need to retain logs for 90 days or longer for compliance, storage accounts are pretty cost-effective. The third option is Event Hub for streaming. If you want to stream logs to external analytics platforms like Splunk or Datadog, Event Hub provides real-time integration. Most production deployments use log analytics for operational analysis and storage account for long-term archival. You can send the same diagnostic data to multiple destinations simultaneously. Now, let me show you the analytics flow for turning the diagnostic data into actionable insights. You enable diagnostic settings on your Azure OpenAI Service, which routes logs to multiple destinations. Logs go to log analytics for querying, storage account for long-term retention, and Event Hub if you need external integration. From log analytics, you build KQL queries to aggregate and analyze the data. These queries let you slice your usage data by deployment, time period, application, or any other dimension. For those queries, you create cost dashboards that visualize spending trends, usage patterns, and anomalies. These dashboards should be accessible to both technical teams and business stakeholders so everyone understands cost and usage. The key insight is that raw logs are not useful by themselves. You need to aggregate them into meaningful metrics, visualize trends, and make the data accessible to people who can take action based on it. For example, you might create a dashboard showing daily token consumption by deployment. If you see a sudden spike in one deployment, you can investigate whether it's a legitimate increased usage or a bug causing runaway API calls. Without this visibility, you would only discover the problem when you get a surprisingly large bill by end of the month. Now, let me show you a practical KQL query for cost monitoring. This query analyzes daily cost by deployment, and let me walk you through it. The first line queries the Azure Diagnostics table, which contains all the diagnostic logs. Then we filter where the source provider equals, let's say Microsoft.connected services. Then we filter where category equals request response, which gives us the actual API request. Then we extract structure fields. We extend the prompt tokens by converting properties underscore d.prompt underscore tokens to an integer. We extend the completion tokens by converting properties underscore d.completion tokens to an integer. We extend deployment by converting properties underscore s.model underscore deployment name to a string. Then we summarize the data. We sum the prompt tokens, sum the completion tokens, and count requests. We group by deployment and by day using the bin function for time generated. This query gives you a table showing for each deployment, each day, and how many prompt tokens were consumed, how many completion tokens was consumed, and how many requests were made. This is useful for cost attribution. You can calculate estimate cost by multiplying token counts by current pricing. You can identify which deployments consume the most budget. You can spot unusual usage patterns like a sudden spike in requests that might indicate a bug or an attack. You would typically run this query daily and visualize the results in Azure Monitor dashboard or Power BI report. This enables cost attribution to specific application components and help you identify optimization opportunities. Now let's talk about what metrics you should be tracking in your cost dashboards. There are 5 key metrics that you should be on every Azure OpenAI cost dashboard. The first metric is daily token usage. This should be a trend line showing token consumption over time. You want to see if the usage is growing, stable, or declining. Sudden spikes indicate problems that would definitely need investigation. The second metric is cost by deployment. There should be a pie chart or a bar chart showing which deployments consume the most of your budget. This enables cost attribution. You might discover that 80% of your spending is in one deployment, which focuses your all optimization efforts. The third metric is cost per request. This is your average cost per API call by deployment and time period. This metric helps you understand the efficiency. If cost per request is increasing while usage is stable, something has changed that's making requests much more expensive. The fourth metric is quota utilization. This is a percentage of allocated TPM quota that you are actually using. If you're consistently at 80 to 90% utilization, you're at the risk of hitting rate limits. You should request a quota increase in that case. If you're consistently at 20% utilization, you're probably over provisioned and you could reduce costs by lowering your quota. The fifth metric is error rates. You should track rate limit errors, authentication failures, and service errors. An increase in rate limit errors indicates the quota pressure. An increase in authentication errors might indicate expired credentials. You should also configure alerting based on these metrics. Configure alerts when daily spending exceeds, let's say, 120% of your average, which might indicate an anomaly. Configure alerts, let's say, when quota utilization is consistently above 80%, which means you need to request an increase. You should also configure alerts when error rates exceeds 5%, which indicates service degradation or misconfiguration. Here's what alert logic looks like in code. This is a cost monitor class with a method called check daily spending. It retrieves today's token usage from your monitoring system. Then it calculates the estimate cost by multiplying the token counts by current pricing rates. Then it checks if estimate cost exceeds your daily budget by 20%. If the spending is too high, it sends an alert with details about actual spending versus budget. This alert might go to email, Teams, PagerDuty, or any other notification channels depending on the severity. You should configure different alert channels based on the urgency. High severity budget overruns might trigger immediate PagerDuty notifications to on call engineers. Quota warnings might go to an email as a daily digest reports. Authentication failures might trigger team messages to the security team. The key is to have automated monitoring that proactively identifies issues before they become major problems. If you're only looking at cost manually once a month, you might discover problems weeks after they have started, by which time you have already incurred significantly huge amount of bills. Now let's talk about production best practices, starting with multi-region deployments. You should deploy Azure OpenAI resources in multiple regions for three main. So the first reason is disaster recovery. If your primary user has an outage, you can fail over to a secondary region. Azure has excellent availability, but no service has 100% uptime. Having multiple region deployment provides resilience. The second reason is latency optimization. You can route users to nearest region. If you have users in both North America and Europe, you might deploy in both East US and West Europe so that each user set gets low latency for both of them. The third reason is quota pooling. You can separate EBM quota in each region, so if one region is really limited, you can shift traffic to another region. This effectively multiplies your available quota. For implementation, you should use Azure Traffic Manager or Azure Front Door to route requests to regional deployments. You can configure routing based on geographic proximity for latency optimization or based on health checks for failover scenarios. If one region is unhealthy or rate limited, Traffic Manager automatically routes traffic elsewhere. The complexity here is maintaining a consistent configurations across regions. You need the same models deployed with same settings. You need synchronized authentication configurations. For stateful applications, you might need to replicate user context across regions. But the reliability and performance benefits typically justify this complexity for production use cases. Another critical production best practice is request timeout configuration. You should set appropriate timeouts based on your use case because different workloads have different latency requirements. So, for real time chat applications, you should use a 10 to 15-second timeout. Users expect quick responses in chat applications. If it takes longer than, let's say, 15 seconds, the user experience has degraded significantly. For background processing, however, you can use a 60 to 120-second timeout. These are jobs where users are not actively waiting, so you can tolerate longer processing times for completion tasks. For batch operations like processing large documents, you might use even a longer timeout, let's say 300 seconds. These are bulk operations that process when resources are available. Here's a JavaScript implementation. You create an abort controller. You set a timeout that calls controller.abort after 15,000 milliseconds, which is 15 seconds. Then you pass the controller signal to your API call. If the timeout expires, the request is automatically aborted. This is important because it prevents your client applications from hanging indefinitely if Azure OpenAI experiences delays. Without timeouts, a slow API call could block your application thread indefinitely, causing resource exhaustion and degraded user experience. With proper timeouts, you ensure graceful degradation. If an API call times out, you can show the user a friendly error message, log the failure for investigation, and keep your application responsive. This is much better than having your application hang while waiting for a response that might never come. Another important production consideration is content filtering, which is built into Azure OpenAI. Azure OpenAI includes content filtering that can reject requests or completions containing certain types of harmful content. The categories are hate speech, violence, sexual content, and self-harm content. Each category has customizable service severity thresholds of low, medium, or high. There are three configuration options available. So the first option is default filtering. Microsoft managed policies are applied automatically. These are reasonable defaults that work for most applications. You don't need to configure here anything. The second option is custom policies. You can define your own security thresholds per content category. If you are building a medical application, you might have different thresholds than general chatbot. You have fine-grained control here. The third option is annotations. You can receive content category scores without actually blocking the content. This is monitor mode. You get to see what would have been filtered, but it doesn't impact user experience. This is useful for understanding false positive rates before enforcing filtering. You configure this through the Azure portal under the content filter section. Most production systems use default filtering with annotations enabled for logging. This provides protection against harmful content while giving you visibility into filtering behavior. One thing to understand is that content filtering can reject your prompts or the model's completions. If a user submits a prompt that violates content policy, you will get an error response. You need to handle this gracefully in your application, perhaps showing the user a message that their request cannot be processed. Now, let me show you what a complete production architecture looks like with all the components we have discussed. The flowchart starts with the application sending a request to an API gateway which handles the authentication and routing. Then the request goes to a token estimator which predicts how many tokens this request will consume. Then it goes to a cache layer that checks if there is already a cache response for this exact request. If there is a cache hit, the cache response is returned immediately with no API call. If there is no cache hit, the request goes to a model router that decides which deployment to use based on complexity. Simple requests go to simpler models like GPT 3.5 deployment. Complex requests go to more complex models like GPT 4 or 5 deployments. After the model generates a response, everything is logged and monitored. The logs capture token usage, latency, costs, and any errors. This architecture includes all the best practices we have covered. Authentication through API gateway, cost prediction through token estimation, cost optimization through caching and model routing, comprehensive observability through logging and monitoring. Building this architecture takes time, but it's what separates production-ready systems from prototypes. Each component serves a very specific purpose in managing cost, ensuring reliability, and providing visibility. So now let me walk you through a practical migration path from a prototype to production over 5 phases. Phase 1 is Basic setup in week 1. You provision your Azure OpenAI resource in your primary region. You deploy initial models starting with, let's say, GPT 3.5 Turbo for testing. You implement API key authentication, which is fine for initial testing. You set up basic logging to understand your usage patterns. Phase 2 is security hardening in week 2. So you migrate from API key authentication into Azure AD authentication with managed identities. You configure private endpoints so traffic stays within your VNet. You enable diagnostic settings that send detailed telemetry to log and analytics. You implement secret rotation if you're still using any API keys temporarily. Phase 3 is cost controls in week 3. So you add token estimation and budget checks before making API calls. You implement response caching for repeated queries. You configure model routing logic that sends simple requests to GPT 3.5 and complex requests to GPT 4. You set up cost monitoring dashboards and alerts so you're notified of unusual spending. Phase 4 is scale and reliability in week 4. You deploy to a secondary region for failover capability. You implement a retry logic with exponential backoff to handle transient failures and gracefully. You configure the traffic manager for multi-region routing, let's say Azure Traffic Manager or Azure Front Door, and then you load test at expected production volumes to validate your capacity planning and identify bottlenecks. Phase 5 is ongoing optimization. You analyze logs to identify optimization opportunities. Maybe you notice certain prompts are inefficient and can be rewritten. You refine model routing rules based on your actual performance. Maybe you discover certain request work types works better fine with GPT 3.5 when you initially routed them to complex models like GPT 4 or 5. You adjust the quota allocation based on usage patterns as your traffic evolves. You iterate on prompt engineering for token efficiency as you can learn what works best for your specific use case. Here's a reality check. Most organizations spend 4 to 6 weeks moving from, let's say, prototype to production ready Azure OpenAI implementation. This timeline assumes you have dedicated resources working on it. Rushing this process typically results in cost overruns or reliability issues that you have to fix later anyway, which ends up actually taking much more time overall. It's better to invest the time upfront to build the right architecture than to rush into production and then spend months actually firefighting issues. Let me share some common pitfalls we see in teams encounter and so that you should be avoiding them. Pitfall 1 is inadequate quota planning. Many teams provision the minimum quota just to get started and then hit rate limits immediately when they go to production. Azure quota increases can take time to process, sometimes even 2 to 3 weeks. You should request quota increases well before your planned launch date, not after you have already experiencing rate limiting errors. Pitfall 2 is having no token estimation. Without upfront token estimation, you cannot predict costs. A high traffic application with inefficient prompts can consume thousands of dollars in just hours. By the time you notice the problem, you have already incurred significant costs. Token estimation lets you identify and fix efficiency issues before they become expensive. Pitfall 3 is ignoring regional differences. Model availability and pricing vary significantly by region. If you deploy in a region that does not support the models you need, you'll be forced to migrate to a different region later. This migration requires reprovisioning resources, updating application configurations, and potentially accepting downtime. It's much easier to choose the right region initially by checking the model availability first. Pitfall 4 is API key management. Storing API keys in application code or configuration files creates security vulnerabilities. Keys might be accidentally committed to source code control, exposed in logs, or accessible to unauthorized users. You should use Azure Key Vault or manage identities from day one. It's much harder to retrofit proper secret management after you have already deployed them with hard-coded keys. So let me summarize the key takeaways from this session. For a setup foundation, you should use Azure AD authentication with managed identities for production deployments. This eliminates credential management and provides comprehensive audit trails. You should enable private endpoints for security and compliance. This keeps your traffic within your private network. You should deploy to multiple regions for reliability and quota pooling. This provides both failover capability and additional throughput. For cost management, you should implement caching for repeated queries. In FAQ style systems, this can reduce costs by up to 40 to 70%. You should route requests to approximate models appropriate models based on the complexity. Not every request needs reasoning model like GPT-4 or 5. You should set appropriate max token limits to prevent overgeneration. Don't let a simple classification task consume 2000 tokens. You should monitor spending daily with automated alerts. Don't wait until the end of the month to discover if you have a huge amount of like a big bill for your cost overruns. For production readiness, you should configure comprehensive logging to Azure Monitor. Visibility is essential for troubleshooting and optimization. You should implement retry logic with exponential backoff for rate limits. Transient failures are normal and they should be handled gracefully. You should test at production scale before launch. Load testing identifies capacity issues before real users encounter them. You should plan quota increases well in advance of deployment. Approval processes can take weeks, so don't wait until the last minute. So here are your immediate next steps to get started with Azure OpenAI. So the first action is to provision your first Azure OpenAI resource in your preferred region. Go through the process we have covered today. It should be fairly quick. The second action is to deploy a test model and make your first API call. Get the hands-on experience with APIs and SDKs. You should actually write the code and see the responses. The third action is to enable diagnostic logging to log analytics. Start collecting telemetry from day one so you have historical data for analysis. The fourth action is to experiment with prompt optimization to understand token efficiency. Try different ways of phrasing the same request and see how token counts change. This hands-on experimentation teaches you what works. For deeper exploration, I have created comprehensive courses at mukulraina.com covering production Azure OpenAI architectures. These courses include detailed implementation of caching strategies, multi-region deployments, and advanced cost optimization techniques. If you want to go beyond what we have covered today and see complete working implementations, these courses on my website do provide that depth. Feel free to subscribe to my channel at Mukul Raina for more Azure architecture content. I regularly publish videos on topics like rack systems with Azure OpenAI, vector database integration, and enterprise AI patterns. Thank you again for watching, and I hope this gives you a solid foundation for implementing Azure OpenAI in your production environments. Thank you.